Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is pumping circuits. Our objective is to examine the ladder logic diagrams of several different configurations of pumping circuits performing common industrial functions. This lecture operates under the assumption you've watched both the 2- and 3-wire magnetic motor starters and the alarm circuit with silence option lectures available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. This lecture examines 6 different ladder logic diagrams. Technically 8, since the last circuit is modified twice to include rudimentary diagnostic capability for the purposes of applying a number of the concepts we've thus far discussed. Keep in mind, I do not expect you at this point in your education to design ladder logic diagrams, but rather interpret existing ladder logic diagrams. Consider this lecture an opportunity to put this skill to practice. Pause the lecture often and see if you can figure out how the system would respond to certain input conditions. Draw pictures, take notes. As you'll recall, magnetic motor starters are divided into 2 general categories: 2-wire and 3-wire control circuits. 2-wire circuits are ordinarily characterized by automatic switches like temperature, float, or pressure switches and are suited for applications in which the automatic starting of the motor would not present a safety hazard. 3-wire circuits, in contrast, are ordinarily characterized by momentary manual switches like push buttons and a holding circuit. A 3-wire control circuit is suitable for applications where the unexpected starting of a motor would present a safety hazard. We'll examine both 2- and 3-wire configurations of motor-driven pump circuits. Let's examine this simple 2-wire control circuit first. This example illustrates the logic behind a motor-driven pump designed to keep a sump dry. The ladder logic is extremely simple. The first and only rung is a series connection of a normally open float switch, the P contactor coil, and the normally closed overload contact. The float switch is physically placed in the bottom of the sump. By all means, pause the lecture and see if you can figure out how this ladder logic diagram implements the function of this electrically controlled system. When the sump is dry, the float switch is in its deactivated open state. However, when fluid in the sump rises to the set point of the float switch, it is actuated into its closed state. The P contactor coil is energized. The primary P contactor closes, and the motor-driven pump begins rotating. After a period of time, the sump will be pumped dry enough such that the float switch reaches its reset value and reopens. The open float switch de-energizes the P contactor coil, the primary P contacts open, and the motor-driven pump free spins to a halt. The normally closed overload contacts serve to protect the motor from sustained overload conditions. If the pump were to jam after sucking up a rat, a crocodile, a hobo, or some other sewer-dwelling beast, the motor driving the pump would experience sustained high current. After a period of time, the overload elements would heat up and the overload contact in the control circuit would open. The open overload contact de-energizes the P contactor coil and turns off the motor-driven pump. Consider subtle modification of this circuit and how the modification affects its behavior. This example illustrates the ladder logic diagram behind a motor-driven pump designed to fill a tank to a certain level. The ladder logic diagram is extremely simple. The first and only rung is a series connection of a normally closed float switch, the P contactor coil, and the normally closed overload contact. This time, the float switch is physically placed at the top of the tank that needs to be filled. By all means, pause the lecture and see if you can figure out how this ladder logic diagram implements the function of this electrically controlled system. When the tank is empty, the normally closed float switch energizes the P contactor coil. The primary P contactor closes and the motor-driven pump begins rotating. Fluid begins filling the tank. After a period of time, the tank will be pumped full enough such that the float switch will be actuated into its open position. The now open float switch de-energizes the P contactor coil, the primary P contacts open, and the motor-driven pump free spins to a halt. The overload contact again protects the motor from sustained overload conditions. Let's step it up a notch and examine the ladder logic diagram of a pumping system designed to pump a certain quantity of liquid out of a tank. This system incorporates two float switches: the lower float switch, LFS, in the bottom region of the tank, and the upper float switch, UFS, in the top region of the tank. The volume of space between the two float switches represents the quantity of liquid that is to be pumped out. Let's assume for this application that fluid stops entering the tank when the upper float switch is triggered. The first rung is a series connection of the normally open lower float switch, the normally open upper float switch, the P contactor coil, and the normally closed overload contact. The second rung is a holding contact, P1, in parallel with the upper float switch. This is an auxiliary contact associated with the P contactor. By all means, pause the lecture and see if you can figure out how the ladder logic implements the function of this electrically controlled system. When the tank is empty, neither float switch is actuated, and the motor-driven pump remains off. As fluid fills the tank, it eventually reaches the level of the lower float switch. The lower float switch closes, however, there is still no path to energize the motor-driven pump. Eventually, fluid rises to the level of the upper float switch. The upper float switch closes, at which point the P contactor coil is energized. The P1 holding contact closes, as does the primary P contactor. The motor-driven pump starts pumping liquid out of the tank. At some point, the falling liquid level reaches the reset level of the upper float switch. The open lower float switch de-energizes the P contactor coil, the primary P contacts open, and the motor-driven pump free spins to a halt. Without the lower float switch, the motor-driven pump would still be energized via the P1 holding contact. Note that if the upper float switch is actuated without the lower float switch being actuated, a situation ordinarily made impossible by both switches being inside the same tank, the circuit wouldn't turn the pump on. This prevents an erroneous or falsely triggered upper float switch from initiating the pumping process. Let's step it up yet another notch and examine the ladder logic diagram controlling a dual pumping system, utilizing 4 float switches at different levels inside a sump. The intention of this circuit is to evacuate a sump using 2 pumps. However, only engage the backup pump in the event of an emergency. Additionally, this system incorporates an alarm circuit, almost identical to the one discussed in the alarm circuit with silence option lecture. This sub-circuit appears in the lower levels of the ladder logic diagram. Note that if float switch 4, the uppermost float switch, is triggered, the buzzer goes off, as does the warning lamp. If you wanted to silence the buzzer, the silence button and control relay 1 and its associated contacts make this option available. The upper reaches of the ladder logic is essentially the same as our previous 2 float switch circuit. One section controls the primary pump P. The second section controls backup pump B. Float switch 1, the lowermost of the 4 float switches, must be actuated into its closed state for either section to even concern itself with starting. This prevents an erroneous or falsely triggered upper sensor from initiating the pumping process. Primary pump P only comes on if both float switch 1 and float switch 2 are actuated by rising liquid level in the tank. If the primary pump P can't keep up with the rising liquid level, or if primary pump P has locked up and gone into overload, backup pump B is turned on when liquid level reaches float switch 4. Note that the holding contacts P1 and B1 in parallel to float switch 2 and float switch 3 would keep that particular pump running until such time liquid level in the tank drops below the reset level of float switch 1. This again allows the backup pump to step in and save the day if the primary pump can't cut it or cuts out. Does this remind you of your relationship with your lab partner? Note the overload contacts for primary pump P and backup pump B are independent from each other. This allows one pump to function even if the other is disabled because of an overload. For this particular application, this makes total sense. However, not all systems require this feature, and some are designed to even prevent this from happening. This is called a common arrangement of overloads, and that all overloads use the common right-hand upright on the ladder logic diagram. An overload condition in one rung does not affect the other. Alternatively, consider contactor coil A and contactor coil B and the switched logic that governs the operation on two different rungs. However, the overloads protecting motor A and motor B are placed electrically in series with one another. If either motor went into overload, both motor contactor coils would be de-energized. This could prevent the whole system from operating if one of the subsystems failed. This is called a series arrangement of overloads for obvious reasons. An overload condition in either motor would de-energize both motors. Related to this topic, note that overload relays, especially older ones, sometimes feature not one auxiliary contact, but rather 3 auxiliary contacts, one for each phase. For very important reasons, a motor starter making use of this type of overload relay must use all auxiliary overload contacts in series with one another. This way, if one or more phases are in overload, the condition is recognized and the motor de-energized. Rather than drawing this schematically as 3 separate overload auxiliary contacts in series with one another, sometimes you'll see one overload contact with words all overloads above it. Finally, consider a contactor coil A and contactor coil B and the switch logic that governs their operation on 2 different rungs. However, the overloads protecting motor A is placed after the overload governing motor B. This is called a cascading arrangement. If motor B went into overload, motor A could continue to function. However, if motor A went into overload, both motor A and motor B contactor coils would be de-energized. This could be used to coordinate the safe operation or shutdown of a system. For example, keeping a fan running if a motor went into overload, however, disabling both motor and fan if the fan went into overload. Finally, our previously discussed configuration of common overloads. An overload in A does not affect system B, and an overload in B does not affect system A. Lest you think all pumping circuits necessitate float switches, consider the ladder logic diagram coordinating the function of 3 motors: a motor-driven compressor, a type of pump, a motor-driven fan, and a motor-driven evaporator and an air conditioning unit. The first rung includes a normally open temperature switch, a normally closed pressure switch with a set value at the lowest pressure the system is intended to operate, called PS low, and a normally closed pressure switch with a set value at the highest pressure the system can safely operate, called PS high. The contactor coil of the compressor C, and the overload contacts for the compressor, fan, and evaporator. Recall from our previous discussion of overload contacts that this is a series arrangement, and that an overload in any one of these 3 different devices would de-energize all 3 motors. Rung 2 is an auxiliary contact of the C contactor called C1 that serves as a holding contact. Rung 3 is the contactor coil of the fan, F, and rung 4 is the contactor coil of the evaporator, E. If the temperature switch detects a temperature above its set point, it initiates operation of all 3 rungs. Rung 3 and 4, governing the fan and evaporator, have no additional controlling logic, and the fan and evaporator primary contacts close. The fan and evaporator start fanning and evaporating as intended. The series arrangement of the 2 pressure switches in rung 1, however, basically keeps the compressor operational only between a certain range. If pressure is lower than the PS low set point, both PS low and PS high are in their deactivated normally closed state, and the compressor contactor coil C is energized. The primary C contactor would close, as would the auxiliary contact C1. Note as pressure rises, it will eventually surpass that of the PS low set point. PS low opens, however, the now closed C1 holding contact in parallel with it keeps the compressor contactor coil C energized until pressure reaches that of the PS high set point. When PS high opens, the compressor contactor coil C is de-energized. The primary C contacts open, as would the auxiliary contact C1. As pressure falls to the reset value of PS high recloses. Pressure continues to fall until it reaches the reset level of PS low, at which point PS low also recloses. The compressor is again energized, keeping pressure oscillating between the PS low and PS high values as intended. Note that as long as temperature switch 1 is closed by an ambient temperature in excess of its set point, the compressor stays inside an operational range, bouncing between low and high set points, and the fan and evaporator keep fanning and evaporating as intended. The coordinated activity of these three devices cools the space and keeps everyone happy. Lest you think all pumping applications are fully automatic in nature, consider a motor-driven pump supplying flow to an electrically controlled hydraulic system. Let's ignore the ladder logic governing the control of the hydraulic components at the top and focus our attention on the ladder logic governing the safe operation of the motor-driven pump. Notice this section of the ladder logic features a holding circuit with momentary contact push buttons followed by three devices: a normally closed pressure switch, a normally closed temperature switch, and a normally open float switch being held closed. Note the arrow modifier. Recall that all schematics are always drawn in their depowered state. The arrow modifier holding the normally open switch closed means that this system is intended to initiate operation with the float switch actuated. This means there should be hydraulic fluid in our reservoir. Consider the implication of these devices in series with one another and their intended function in this circuit. If the e-stop and all three automatic switches following the holding circuit and momentary contact manual push buttons are closed, the manual switches do exactly what they say. If an operator presses and releases start pump, the P contactor closes and the P1 holding contact maintains this last asserted state. If an operator presses and releases stop pump, the P contactor opens and the P1 holding contact drops out. If, however, system pressure, as indicated by the pressure switch, exceeds a given value, the normally closed pressure switch would open and de-energize the motor-driven pump and disable the operator from starting it until pressure dropped below the reset value. This electrical pressure switch, in effect, backs up the hydraulic pressure relief valve should the pressure relief valve fail to limit maximum working pressure. Similarly, if fluid temperature, as indicated by the temperature switch, exceeds a given value, the normally closed temperature switch would open and de-energize the motor-driven pump and disable the operator from starting it until the fluid cooled. The temperature switch prevents fluid degradation due to overtemperature conditions. Finally, if the fluid in the hydraulic reservoir ever dropped below the reset value of the normally open float switch being held closed, the float switch would return to its normally open deactivated state. The open float switch would de-energize the motor-driven pump and disable the operator from starting it until fluid is replenished. The float switch therefore prevents the hydraulic system from pseudocavitation by sucking in air from the depleted reservoir. The ladder logic controlling the motor-driven pump therefore serves several purposes. 1, it only runs the pump when an operator calls for it, and 2, it protects the system from overpressure and overtemperature events, as well as from low fluid levels. Notice, however, if an operator were to press and release start pump, and the pump didn't start, there could be several reasons why, and an operator could only guess at the reason. Is the e-stop open? The stop pump push button stuck open? The start pump push button not closing? The motor overloaded? The pressure too high? The temperature too high? Or is the fluid too low? Notice there's no feedback, and an operator is going to scratch their head and say, "Don't work," on their maintenance requests, giving you, the technician responsible for returning this pump to service, no clue as to what to expect. It is for this reason ladder logic can also be used to perform diagnostic services. Consider this ladder logic diagram offering rudimentary feedback about the state of this system. Note that the pressure switch, temperature switch, and float switch now utilize additionally mechanically interlocked switches that energize pilot lamps that give visible indications of the nature of the problem. Note the mechanically interlocked pair of switches turn off the pump and turn on the appropriate warning light. If system pressure is in excess of the set point, the normally closed side of the pressure switch opens, de-energizing the pump and disabling operation, and the normally open side of the pressure switch closes, energizing the pilot lamp that says overpressure. Similarly, if fluid temperature is in excess of the set point, the normally closed side of the temperature switch opens, de-energizing the pump and disabling operation, and the normally open side of the temperature switch closes, energizing the pilot lamp that says overtemp. Finally, if fluid level drops below the reset value of the float switch, neither side of the switch will be held in the activated state. The normally open side would reopen and de-energize the pump, and the normally closed side would reclose and energize the pilot lamp that says low fluid. Alternate methods exist that do not necessitate the use of mechanically interlocked switches. Consider this implementation, that rather than the pressure switch, temperature switch, and float switches directly inhibiting the P contactor coil from closing, 3 control relays and their associated contacts indirectly do so, as well as give visible indications of the nature of the problem. Note that the pressure switch, temperature switch, and float switch all selectively energize or de-energize an appropriate control relay coil upon closure. When energized, that particular control relay's associated contacts would change states. If PS1 detected high pressure, it would energize the pressure relay coil, PR. The associated PR1 contact would open and de-energize the P contactor coil. The associated PR2 contact would close and turn on the overpressure pilot lamp. If TS1 detected high fluid temperature, it would energize the temperature relay coil, TR. The associated TR1 contact would open and de-energize the P contactor coil. The associated TR2 contact would close and turn on the overtemperature pilot light. Finally, if float switch 1 registered unusually low fluid level in the reservoir, it would close and energize the fluid relay coil, FR. The associated FR1 contact would open and de-energize the P contactor coil. The associated FR2 contact would close and turn on the low fluid pilot lamp. It may seem that this implementation uses more hardware than that of the mechanically interlocked switch pairs. However, realize hardwire relay-based ladder logic is being replaced with programmable logic controllers, PLCs, that can utilize programmed virtual elements to serve the purpose of physical relays. This implementation utilizing relays might be better suited for a PLC, since it would actually use less hardware, wiring, and 3 non-mechanically interlocked switches. We'll discuss PLCs and PLC programming in later lectures. Alright, this about wraps up our examination of various pumping circuits. Again, keep in mind at this point in your education, I am not asking you to design ladder logic diagrams. All I'm asking you to do is be able to interpret existing ladder logic diagrams and determine the response given various input conditions. My intention in this lecture was to serve as a guide for representative samples of ladder logic diagrams performing common recognizable industrial functions utilizing some of the concepts and devices we've thus far discussed. In conclusion, this lecture examines several different types of pumping circuits performing common industrial functions. We looked at a sump pumping circuit using a float switch at the bottom of a sump, a tank filling circuit using a float switch at the top of a tank, a pumping circuit designed to pump out a quantity of fluid using 2 float switches at different levels, a dual pumping system that coordinated the efforts of a primary and backup pump using 4 float switches and an alarm circuit, an air conditioner circuit coordinating the activity of a motor-driven compressor, fan, and evaporator, and finally, an operator-initiated hydraulic pumping circuit that disables the pump in the event of overpressure, overtemperature, low fluid, or overload conditions. We had a brief discussion of overloads common with each other, in series with each other, and in a cascading arrangement with each other. Finally, we examined 2 types of diagnostic circuits that both serve to turn off the pump and turn on an appropriate warning light. one utilizing mechanically interlocked switches, and the other utilizing control relays and associated contacts. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.